Shall we start?
Yes.
Okay, so you remember last time we were looking at mountains and their slopes, and we also introduced the concept of local maximum and local minimum. And you remember the condition that a point has to satisfy to be a local maximum is that the slope at that point has to be 0. You remember, if it is a local maximum, it's flat here on the top. So the tangent will be horizontal. So the slope is 0, and the slope of the slope. So if you were to plot the slope, and if you look at the slope of the slope, you remember the condition that has to be satisfied? Somewhere here. Okay, let's see. Okay, looks like it's lost. No, let's see. Yeah. Yeah, here. We had a local maximum, and you see the slope is negative, right? And for a local minimum, of course, sorry, not the slope, slope of the slope. Slope has to be 0, it's flat here, locally it's flat, horizontal. But if you look at the slope function, this is giving the slope of this. The slope of the slope is positive. Okay, that is what we had talked about last time.
Yes.
And till now we have not even bothered to make these things very precise, what I mean by certain concepts. I am still building intuition, and before I start writing down equations, it will be nice to, any problem? It will be nice to have two more concepts which you will encounter in the course of the study, and they are fairly easy, so even a child can roughly see that that is what you should expect. So let me tell that. Okay, I think that's page number 9, that's 10. So imagine some.
We focused.
What? That is fine.
We've locked the focus.
Now it's focused. Is that okay?
Yes.
Okay. So imagine some curve. Okay, I hope by now you have realized that whatever I am saying is not specific to hills and mountains. I mean, who cares whether this curve is giving you height of a mountain. It could be any function. This is x. Instead of height, it could be any function, right? So it's giving you the value of the function at different points. Okay? So whatever I'm saying in this lecture and the previous two lectures, whatever I have said, those observations are going to be applicable not just to mountains and hills, but rather to all classes of functions. Okay, so let's now talk about those two concepts which I want to say. So imagine, okay, that's good. Okay, that's x-axis. Imagine again I am looking at height of a mountain, or if you are okay with it, I'll just write some function f of x. If you are not very happy with f of x, keep imagining f of x as the height of the mountain at point x. Okay, and imagine it has this shape. Okay, now what I am imagining is that, let's say this is some point, let's say it's 1, it's 0 here on the vertical axis, and this is also 1. Okay, now what's the slope here at this point? Slope is the slope of this line. Okay, what's the slope here? Slope of this line. Okay, so forth. Slope of this line. So it keeps decreasing, becomes 0, then starts becoming negative. Okay, now you see that if the value of function here and here are equal, then the curve is such that at some value of x, the curve is going to be flat or will have a slope 0. Okay, if you are okay, so that statement probably it's not very clear, so let me give you another example and then it will be clear why what I am saying is correct. Let's take another function. Okay, let's start from point A. That's x-axis, that's B. So I'm going to look at the function between these 2 points A and B. Okay, and suppose the function has value here at x equal to A, some value which I called f of A. Okay, that's the value of the function here. I hope it's recording. And then the function goes like this, and that's B. Okay, or even maybe a better one would be, let's say, okay, every time I'm drawing the same thing. Okay, so let's change the point to B. That will be a better thing to do. Let's say B is here. That's B, that's A. Okay, that's B. I'm looking at the function within this region. Now you see, slope has some value, it keeps decreasing. But here the slope at no point becomes a 0. It doesn't become flat anywhere. Okay? Now I'll give you, so you have this in mind. What is the value of function here? fa. What's the value of this? fb. Okay? And fa is not equal to fb. fa is this much, fb is that much. Let me give you another curve. So at point A, suppose you have the value of function is this. Okay? Let's look at this region. This is B. Now you see, at some point, the value of function, the slope of the function is 0. It's horizontal. But then there is another point you see. If I look at this, draw a horizontal line, then you see whatever value the function has at point B, there is another point at which the function has same value, which is this. Right? So if within that region the function has equal values, if there is some point A and some point B within the region where you are looking at, okay, at which the function has same values, then it has to, let's say, the shape of the curve is like this. So it goes down, the value, the mountain height goes down or the hill height goes down, it is coming up. So at some place it has to become horizontal. Similarly, if let's say height is 2 kilometers and it increases and it comes back to 2 kilometers, at some point it has to be flat. Okay? It cannot be. So if you don't agree with me, if you try drawing a diagram, try drawing a curve in which the function has equal values at two ends but never becomes horizontal. Okay, never becomes flat. Keeping a condition that mountain is smooth. It should not have this kink. then of course this is on the top, it's not flat, right? So if you understand that, then I will tell you another thing. Now another surprising thing. My lines are very bad. So let's draw a line. Okay, for some reason it's yellow. Okay. Now, oh, this is nice. So suppose at point A, is this looking fine in camera? Suppose at point A, okay, this will not work. These two, and then we go back. Let's x-axis. That's point A, that's point B. Here is the value of the function fa. So function has value A, fa at A, and at B some value fb. Okay? So let me draw like this. Okay, I'm only interested in this region, A to B. So let's do one thing. Let's take this and okay. Okay, sorry. So this point, so I should shift it here, but you can imagine that is fa. Okay. Now, here is the claim. I'm going to connect this point with that point. Okay, let me use some color. Okay, let me use green. Green will be visible. Let's see. Is it visible in the camera? Okay. I've just connected this point which is on the curve corresponding to x equal to a, and that point which is on the curve corresponding to x equal to b. Okay. Now that's a straight line that has some slope, whatever slope it has. You can almost see that if you draw tangents at different points on this curve, it's here, here it is different. At some point, you will have a tangent which will be parallel to this line. At some point on the curve, you will have a slope that will be equal to the slope of this line. Okay? Is that something obvious? If you are, let's have another one. Let's say, okay, let's draw another one. So again, I want white. Let's have another curve. Let's say, okay, let's say you have, oops, let's say you have, okay, this curve. Now let's again connect the two ends on the curve and get a slope, and I want to use what, green color. So this, okay, this is another curve. I've connected these two. Now look here, slope is this slope here is the slope of this line. So when I say slope is this, what I really mean is the slope at that point is equal to the slope of the tangent I am drawing at that point. Okay, so here the function has a slope given by the slope of this line, so and so. And you see at this point you can see the tangent is going to be this, right? That's the tangent, and you see it's parallel to this green line, correct? That's going to happen always. A good exercise will be not to trust me and try to draw a curve and see if you can violate this, and you are going to discover that you can't. this observation that I have made is called mean value theorem.
And if we have some maximum minimas in between the endpoints, local maximum minimas?
So, I mean, let's say, let's take, shall I remove this?
Yes.
Okay. Okay, this doesn't go away, so that doesn't help. Let's go to next page. So, it's always confusing. So we are using white. Is it straight? Yes. X, some function. Okay, if you don't like, you still continue thinking of a mountain, and so you want a maximum minimum now. Is that okay? Is that what you want?
Yes.
So now, what's the question?
Still that is true? That the claim which we have made in the last?
Yes, that's true. So let's say, so that's A and B. If I look at this point, that's the value of the function. So let's
we have to join the endpoints.
yeah, let's join it. We want to join these. So let's say I join them and get this. Okay.
Yes.
So what's the question? There will be some point on this at which slope will be like this one.
Yes, parallel to this.
Okay, and you can see this point, right?
Yes.
It has to have that slope. Correct? See, slopes could be different at different places, but the claim is not where it will be. There will be some point. And you can make another observation. So you say, okay, good. If I look at this interval, okay, within this you can find two places where the endpoint, the values are equal. Correct? So it will be flat at some point.
Yes.
If you take a different point, see, our claim is about when I join the two points, okay, choose arbitrarily point A and B, connect those, whatever slope you get for that line that you have obtained, right? There will be some point where the slope will be equal to this.
At least one.
Actually, there could be more, yes, at least one. Is that okay? So that's mean value theorem. So as I said, we will come back to all this later in more detail, but I believe now we have good intuition about the kind of concepts that we are going to encounter in the study of calculus. Okay. Now slope is so central to our understanding of calculus that let's have a good understanding for slope of a line. Okay, you already know its equation, you already know something about it, but I want to be sure that you know what needs to be known. Okay. So understanding slope a little better, a little more. Okay, so I'll give you a straight line. Okay, so I give you some straight line, that's x. Okay, now I will not be attached to mountains and hills. I plot on this axis some function f of x along this, the independent variable x. Okay, and let's mark some equidistant points. I'm not sure whether I can mark equidistant points. So let's say this. So that's some point. Okay, you have to tell me whether it is looking. Do you think this is equidistant? Looks like. Fine. Is that okay? Okay. Also, let's have some dotted points. So on the vertical axis, I have. This is cool. Okay, I hope it looks perpendicular. Okay. So that's f of x, that is x. Now you can see from here that if you go from this point to that point, okay, the value of function changes from this to this. Yeah, you can leave it here. The value of function goes, so let's say this point is A, this point is B, C, D. Okay, this is f of A, f of B, f of C, f of B. Here these intervals are equal. So A, B, the distance between B and A is same as distance between B and C, same as distance between C and D. Okay. Now when you go from A to B, the value of the function goes from FA to FB. What's the change in the height of this function, value of function? The change is this much.
FB minus FA.
FB minus FA. Okay, that's the change. When you go from here to there by equal amount meaning as it was AB, distance between A and B, the difference in this height and that height of the function, okay, value of function FC minus FB, this difference, this you can argue or you should see that these are equal. In this picture it's not looking good because there are errors, but this height is same as that height, which means a straight line is a function or is a curve whose rate of change per unit distance or per unit displacement along the x-axis is independent of where you are looking at. Are you following? Okay? Meaning in equal intervals, the height increases or decreases by equal amounts, no matter where you are. If this is not so clear, then you can think of this. Take another curve. Okay? Take another curve. That will be clear. Look at this. At point A, this is the height. Okay, that's the height. At point B, that's the height. That's the value of the function. At point C, it is this. Is that correct? Yeah. At point D, you see here, there's a big jump. Here it was much smaller jump. So as you go from A to B, this is the change in height. As you go from C to D, you have this much. Let me give you another curve, which will make it better, I guess. Let's choose, not this, sorry. Okay, let's take even more dramatically increasing. So let's go like this and then suddenly like this. Now you see, as you go from point A to point B, your function changes by this much amount, right? So let's say this is 1 kilometer. In 1 kilometer, the height of the mountain has increased by, let's say, 100 meters. But when you are at point C and you go to the next 1 kilometer, at point C, what's the value here? It's here. And at point D, the value is here. You see? When you go from A to B, the increase in height is this much. When you go from C to D, the increase in height is this much. This, for this function, the increase in the values of the rate at which the value of the function is increasing depends on where you are. But for a straight line, it increases by equal amounts. Okay? Which also means that if you take a straight line and you, let's say, go from A to B, it increases by, let's say, whatever amount. Then you go from A to C, it will increase by double the amount. If you go from A to D, it will increase by triple the amount. Okay? So it's increasing linearly. That's why it's called a linear function. Okay? So I hope this is all clear. Is this fine? I will show you by an equation now, because you know that equation. So let's say y, I don't like it, y is equal to mx plus c. Okay, you already know about lines, so I'm not going to say a lot, but I just want to draw your attention to some point. Take a point x1. Okay. So what we are doing is x, y, you have some, I don't know why it happens, and you take this straight line which is given by y equal to mx plus c. Okay. Now take some point x1, take another point x2. Look at what is the value of function here. It's y1. Okay, so that is y1. Here it is y2. Is it fine? So at x1, this equation, the point on this curve, on this straight line, satisfies the following. y1 is equal to mx1 plus c. Is that okay? Okay, because this point is on this line, so it has to. Okay, what y1 is that? At point x2, okay, I think if I have pen in my hand, then there's a problem. y2 is mx2 plus c. Let's look at the increase in height, this much, this object, this height. What is that? This is y2 here. Value of the y is y2, and here it is y1. Okay, it's y1 here. Sorry, I am writing as y2, and this is y1. So I want to know y2 minus y1, because this height is y2 minus y1, right? This is from here to there, it's y2 minus y1. So what is y2 minus y1? I subtract the 2. From there I get y2 minus y1 is equal to m of x2 minus x1, and c cancels out. So you see, y2 minus y1 divided by x2 minus x1 is equal to m. Okay, what is the left hand side? Left hand side is the change in height per unit displacement. You take the distance between x2 and minus x1, you divide it by it, so it's per unit. So the rate of change of height, or rate of change of value of the function per unit change in value of x is a constant. Forget about that it is m which is there. It's a constant, meaning it does not depend on where you are looking at. Because if it did, then this ratio would know, and the right hand side would be a function of x1 and x2, right? So I have convinced you by this, is this clear, that the rate of change of value of function per unit change in the value of x is constant for a line, okay, and that will not be true for a curve which is going very, any other curve, it will not be the same, and we have seen some examples, okay. Good. So what next? Let's see, just a second. Very good. So we will stop here and continue with next topic next time, and it will be the derivative which we are going to introduce.